Hello, everyone. Welcome to MIF++. It's a pleasure to introduce Professor Mikkel Juelsholt, who will talk about continued challenges in high-throughput materials prediction. Over to you, Mikkel, please.
Yes. Thank you so much. And thank you so much, everyone, for being here. So, yes, this is the first time I'm going to be talking about this. I'll start by see if I can change my slides. I can. So I'll start by a disclaimer and say I'm not a computational materials scientist, chemist in any way. I'm an experimental materials chemist and a pretty okay crystallographer. Which turns out to be quite important for verifying these output of computational models. So this is the first time I'll be talking about this, but so the talk today will basically be based around this preprint I put out June this year on some of the challenges in these high throughput materials predictions, specifically some problems for this model developed by Microsoft, which they call MatterGen. So we'll see where it takes us. There's both some, what should we say? There'll be the paper and then some other insights which didn't make it really into the paper, but hopefully it'll be somewhat useful. Just so we are everyone on the same page, right? Why do we need high throughput materials prediction? Well, for materials, we're generally interested, of course, in making materials that have some properties. For that, we need to make materials that have the atoms put together in the right way. And we need to also be able to synthesize them. So that gives us this nice little relationship between synthesis, structure, and properties. And basically, there's two questions we need to answer, right? Which material to make and how do we make them? And the big problem for both questions is, of course, that the periodic table is really big. There's a lot of materials we can make. And going through every single combination of the periodic table that we want to try, well, that's going to take way too long time to do. And of course, it's an even bigger problem then because you can synthesize the same material in many different ways. So it's an even bigger problem for the synthesis side. But just figuring out what to make, we're just basically limited that there's too many things to try, right? And this is where computational work comes into the picture, right? That we basically need to know what we're trying to make and also ideally how we are trying to make it before we even go into the lab. But of course, as I think a lot of you know way better than me, there's a lot of well-known issues with trade-offs between the accuracy and the speed of like classical computational approaches. And this is where a lot of people have tried to be moving into AI, machine learning, by combining ideally both theory and experiment and then accelerate the discovery of new materials through that. And there's been a lot of work on this, but I think the three like really defining papers is these three papers, two of them in 2003 by Google DeepMind, and then a paper from Berkeley where they used this autonomous lab, and then of course this paper in 2005 by Microsoft, all of them in Nature. And just to set the stage for where the Microsoft paper come in, right, was there was first this paper by Google DeepMind that had developed a model to predict, they said 2.2 million new structures, which represented, and what they say represent an order of magnitude expansion in stable materials known to humanity. And then this autonomous lab in Berkeley, they claimed that they could synthesize. I hope it's the right number, but I've written 41, so I hope that's the right number. And of course, as we have some of the co-authors on the papers here, people started then criticizing and say, well, these these models that don't work, right? So the first thing is computational prediction is not equal with discovery, right? Like just because a computer says it's real doesn't necessarily mean that it's real. Then, of course, if you are going to make them real, you need to make sure that you show that you have made the right material. You can't just get the right diffraction pattern. You also need to get the right composition. And of course, you need to you can see this is not a very good fit for a Nature paper. You should probably make sure that your fits are really good before you claim you have made a new material. And I think the biggest impact that really maybe shook every part of the field a little bit was this insight that DFT, which is like, I think, the common method to look at predicting stable materials, is that they have an enormous problem handling disorder in these handling this like occupational disorder in materials, and therefore DFT has this tendency to, instead of predicting high symmetry materials where the atoms are sharing the same crystallographic site, they're split over. The atoms are uniquely sitting on what the DFT wants to say is unique crystallographic sites, but in reality, you can lower the symmetry quite substantially by having the atoms sharing the sites. And yeah, there's some examples here, right? And of course, that means that if you train an AI on DFT data that suffers from this problem, well, you're going to get this problem with your AI will predict a bunch of low symmetry, really well-ordered structures, which in reality would be disordered high symmetry structures. And so this is kind of where MatterGen from Microsoft is kind of the new step on this. It was published, I think, January this year. And after that, my response came into it. So basically, MatterGen, they made an AI, they call it diffusion model, or it is a diffusion model, which is trained on structures from this materials project, which is this big computational database, and then this inorganic crystal structure database, ICSD. And it's in principle a really cool model, right? You can say we want a material with a given property. They in the paper they look a lot of hardness and magnetism, and then MatterGen will predict a whole bunch of structures that give you some good properties, what you're interested in. And so they say, well, let's see, we can also make these materials. So one of the things that they claim to do is that they synthesize this tantalum chromium oxide in a disordered form. But again, what is it called? The models start by predicting it in an ordered form, but they synthesize it in a disordered form. And so just to delve into some of the problems. So this was not in the preprint, but this is just to show some of the issues. So this is all the experimentally verified space group in the ICSD. And this is the distribution of space groups in the publicly available structures on GitHub from the authors. And as you can see, again, basically all of them are these really low symmetry space groups. I hope you can see, but this is P1, number one, right? So they're basically all triclinic or monoclinic, and that's not how we would expect them to distribute if this was like real materials. And to be fair to the authors, they're completely honest about this. The best examples, which is what I do highlight in this paper, right, is that they have all these manganese oxide structures. You can see the papers that they choose to show, the structures that they choose to show in the MatterGen papers are a lot P1. This one is tetragonal. But they're basically all just versions of a Roxol structure. So this is a structure predicted by MatterGen with the unit cell outline in white, and you can see, well, if you disordered, in this case, the manganese and the iron atoms over all the atomic sites, well, you can just make it it's just two Roxol unit cells. So you just elongate the Roxol in one direction. And the authors are completely honest about that this is also a problem that their model suffers from. That this is one problem that it has. The really interesting thing, and where the big problem I think comes, is that MatterGen suffers from what I think is called data leakage, but someone correct me if this is not the right terminology. But the problem is that Microsoft claimed to make this model, which they they claim to synthesize this material, tantalum chromium oxide, and basically they say, well, as I said, it's not an order, it's a disordered version. And it has this rutile structure. And where I come into the picture, I really think was that I looked at this and was like, has no one really ever synthesized a rutile oxide with tantalum and chromium? I was kind of skeptic about that, because that seemed a really simple compound to synthesize. And it turned out, well, the answer is yes, people have done that before. It's back in 1972. There's this Russian team that have this structure here, which is at tantalum, chromium, and 1-to-1 spinel oxide. And it's even a part of the ICSD, right? And the ICSD was a part of the training data set for MatterGen. And I think this was really the big problem, right? That that MatterGen predicts this that this is a new material, but in reality it's not. It's actually something that MatterGen has seen before, which kind of defeats the whole purpose, right? So the question is, of course, how can you miss this? So the first thing is, of course, that the basis, like the setting for the unit cell, is not the same. So this is the structure reported by Microsoft and MatterGen. This is the original structure reported in 72. And you can see very easily, if you look at the elongation of the oxygen bonds, they don't look the same, but it turns out you can do a 90-degree rotation around the crystallographic z-axis, and then you get the same. And also, this is also, if you then expand these two structures into a P1, so we can see so we can kind of look at all the atoms in the unit cell, you can see that all the atomic positions are very, very similar. And it turns out with an error on the data, these positions are the same. So there's no errors on this one, but with an error, these coordinates are all the same. So it's the same material, right? And the problem is that the computer gets confused for various reasons. The question is, I say, yeah, well, how could it be missed? There's also this thing about the composition, right? They say, okay, they have twice as much chromium as they have tantalum. The problem is that their analysis suffers from a really big flaw, which is that in this refinement, they have set the By-Waller factor, which describes the thermal vibration of the atoms. They've set that to 0, which means the atoms in this structure impossibly does not move, or at least in this structure, impossibly. And we know this is not possible, right? Even at 0 Kelvin, atoms will always vibrate. And this is, of course, a big problem when you do a refinement, because occupancy of atoms and the By-Waller factors, they're correlated quite heavily. So we can go and do a correction, and that was what I did. And it turns out that you actually get something much, much closer to the reported material, right? So we can say, what went wrong, right? Well, we continue to see this problem with DFT methods, and AI trained on DFT is simply not very good at handling compositionally disordered crystal structures. But there's also this problem about that the atoms do not care about the crystallographic setting. Like, crystallography is a language we have invented to describe crystals. But computers really care about it, right? So a classic example of this is if you have a hexagonal structure versus a rhombohedral you have a structure that can either be in a rhombohedral setting or hexagonal setting, right? This is the same atomic structure. The atoms are corresponded in the same way, but it looks very different even to us, but it will also do for a computer. And of course, atoms move. We have to remember that atoms move. The biggest problem, which I always want to, when I talk about this, want to call out, right? This is a really, this is a really huge failure of the peer review, because like a minimum expectation from any peer review journal is that the crystal structure is checked for correctness and unphysical. So it's not enough to look at the R factors. I also ran this CIF file reported by in the Nature paper. I ran it through CheckCIF, which, if people don't know what that is, CheckCIF is a program by the International Union of Crystallography, exactly developed to check if CIF files are real and physical and these kind of things. And CheckCIF actually doesn't catch this mistake. And so the big problem is, right, this is a Nature paper where the authors claim to have discovered this new crystal structure, and like such a basic error goes through. The big question, of course, what happens in all the other Nature papers where the crystallography might not be the most important part, how much actually slips through. And I think I'll come back to this problem with things slipping through peer review later on. So another couple of things I just want to point out. This is not in the preprint. There are some more structures that they reported, which I think is I think it's a bigger problem than just this one example that I have. So one example is this. So the MatterGen, they report this manganese nickel oxide in an R3. This is a real structure, which is an R3 bar. And if you look at these structures, right, you have these two octahedron edge face sharing on top of each other, and then you have two other octahedrons here. So you can see these structures, they're really similar. I think they're the same, but so if somebody wants to go hunting for like other crystal structures that might be present in the training data set in both ICSD and in MatterGen, I think there's more than one. I just haven't been able to find the the real crystallographic way of doing it, but just to be warned. Another thing I just want to point out, which is also not in the preprint, but I always think is funny. So MatterGen, they also said, well, they claim they rediscovered these 101 structures in the ICSD, which were not a part of their training data. And Google DeepMind's paper, they said, well, they predicted these 736 experimentally realized structures that was not a part of their training data. And I want to always, when we discuss this kind of thing, I always want to ask the question, is this impressive at all? Because people mention these numbers and say, oh, we're so good, that means our model is good. So I want to introduce you to an AI I have developed. It's not published yet. It's trained on training data from 1938, which means we can take all structures after 1938 to benchmark this model. It can be run locally on a 2003 MacBook Pro. It takes a couple of hours to run, so it's not very computationally heavy, and it can predict, more than 4,000 structures. And so you might think, how can I do this? How does this work? Well, the way it works is that I've taken data from this book published in 1938 about the oxidation states of the elements. And then we just assign a common oxidation state to all elements. Then we generate compositions where the overall oxidation state is 0. And we just let it check, has this composition been generated before? And if it hasn't, we just count the ratio between the cations and the anions. If the ratio is 1:1, well, then it's a rock salt structure. If it's 3:4, it's a spinel, and then you can keep going with all sorts of known structures. And you might ask, of course, is this useful? And the point is, it isn't, of course not, right? It's not a very good model. But it's a really important reminder that it's not that difficult to guess stable compounds if you guess a lot. The difficult part is doing it over and over again every time, right? To be able to do it with high accuracy and precision all the time. But so my point is, if you guess 2 million times and you just do it with like 10% probability of getting it right, this was what Google did, right? You're going to guess every experimental structure that we ever know. If you just guess 2 million times with a 10% probability for getting it right, you're going to guess every single known structure. So it's like, we have to be aware that when we do these models, predicting a very large number of structures and get a couple of hundreds correct is not very impressive. It's very easy to build models that can do that. So ideally, if you want to benchmark your AI, you should take like 10,000 structures. And if you guess 1 million times, you should ideally basically get all of them back again. Otherwise, the AI is just not that good. So there's a little joke model, but I hope that it's give some perspective on how do we actually benchmark how good these models are. So then the question, of course, what can we do to improve? And the thing is, we have to be honest about our capabilities, but also ourselves, of course. So this, I hope I don't piss off too many people now, but I think the first thing to realize is that DFT and other computational methods, they are not that great. Like, they are not terrible, but they don't get it correct 99% of the time. And that's going to be a problem for any AI you're going to build. Of course, it also means if you struggle with crystallography, you have to be careful about working with materials. Crystallography underlies like everything we do, unless you're working with amorphous materials. And so my main advice, if there's any students listening, take a crystallography course if you want to work with materials. That's really how you avoid making these kind of mistakes, so your Nature paper doesn't get attacked by people like me. But this thing about computational tools, right? It doesn't really matter if they're correct 20 or 80% of the time, right? The problem is an AI where 20%, sorry, of your training data is wrong is not going to outperform that, right? It's not going to outperform that. So if you want to make a good AI, you need to make sure the training data is bad. And in this sense, what I also write in this preprint is that generating 1,000 structures where we need to find hundreds of structures that are simply wrong is not a very good AI, right? Like it's not such a good way of using it. With that being said, now I was really mean to computational tools, and I'll just point out also that I'll now be mean to the experimental literature as well, because the experimental literature is not that good as well. So MatterGen was trained on ICSD, and I'll just want to point out why that is also problematic. So ICSD contains around 300,000 experimental entries, and a lot of them are not very good. So these are some numbers I pulled out earlier this week. So you can, if you go in and you can look this up in the comments on all the entries on ICSD, around so 67,131 of them does not list the R factor, which is this statistical analysis of how good is the fit quality. So it doesn't mean that more than 20% of the structures in ICSD are statistically wrong. It just means that there's a possibility that they are, right? And you have to be aware of that. I also showed you earlier on how important temperature factors are for getting correct refinement. And you can see that it's only 207,469 of them, at least as of this Tuesday when I look these numbers up. They are marked as having temperature factors available. And it doesn't mean that 30% of the structures are wrong. It just means that there is probably quite a lot of thousands of structures where the refinement is actually wrong because people have not managed to make sure that their refinements are physical. Other things you can find if you want to look for it, a classic one is finding stuff like oxides. In this case, this is a tungsten oxide. You can look up this structure in ICSD, and the structure does not contain any oxygen atoms. This one is also really good. So these are some niobium oxide structures. They come as two different entries. You can see two different unit cells. And none of these structures are real. They are part of like the commensurate parts of what we call an incommensurate crystal structure. In this case, this niobium oxyfluoride. So it's important to be aware also that the ICSD is full of all sorts of bad things. Some modern things, if you want to look at some modern things that really happens a lot. I'm not going to point out any, I'm not going to, have any examples of that you can try to look up this yourself. I don't want to be that mean to individual authors, but some really classic mistake is that if you only have one diffraction data set, so one X-ray or only neutrons, if you're trying to refine more than two occupancies on the same crystallographic site, the output will be meaningless because everything will correlate. This is a really classic thing to do, so you can try to look that up. Another modern classic is not taking care of these temperature factors. So for example, having the same atom in two different crystallographic sites, and then have massive differences in the Biwala factor. So, atoms that weigh the same, unless they are in radically different bonding environments, they're going to vibrate roughly the same amount. And because they correlate with the occupancies, it's very easy to get a wrong refinement there. So these are some other stuff that you can kind of look at. So just some conclusions. I've been really fast. I hope that's okay. But yeah, so if we just talk about MatterGen, MatterGen have at least some trouble with separating training data from new predictions, which of course is a really big problem for an AI model. It doesn't necessarily mean that MatterGen is like completely terrible and we can't use it for anything, but we just have to be really aware of it, that this is a problem for the model. And you really have to be careful, especially when you are dealing with compositional disordered materials. But like predicting thousands of new structures with this model is just not a very good way of using it, because you have to manually check everything that they're correct, right? Because it might just be former things. And as always, crystallography characterization is really difficult. It's not just that straightforward, even though it might seem like it. So make sure that you know what you're doing. And then some more general thoughts about this. I think my main takeaway from coming a bit from the outside, not really working with these kind of things, I think there's sometimes an idea that we have this great treasure trove of experimental and computational data, and it's just waiting for a great AI to do all the to dig out everything out of that. I think that's a completely wrong way of looking at it. I think it's important to realize that we actually have a lot of really terrible data. And the really big problem is that we have to figure out what is the good data and what is the bad data before we can even start making these AIs. And I hope to show you that this doesn't just go for the computational part. It definitely also goes for the experimental part of the literature, right? So if we really want to do this accelerated AI discovery in the future, right, we need better computational methods where we can be sure of the output in a much higher degree than we are now. And of course, we want to make sure that stuff like, having atoms that doesn't move at room temperature, it cannot slip through peer review, but it has a lot, right? These kind of mistakes, they have slipped through peer review a lot. So we have to also make sure that we have much more robust experimental work in order to do that. And with that, I was very fast. I hope that's okay. But just some acknowledgements. Yeah, so this was some work I did while I was at a fellowship in Colombia. But I have now moved to Germany, which means the time difference is not as extreme anymore for this talk, which is very nice. But yeah, now I'm funded by the Alexander von Humboldt Foundation, yeah, in Germany. And as a final thing, before I'm happy to take any questions, I want to stress I was a little bit mean and saying every data and everything is really bad. I want to stress that I'm not saying that everybody's work is terrible and I'm this genius that is better than everyone. I also make mistakes for sure. I just think it's important to articulate this thing that there are a lot of mistakes being made in the literature, and if you train your AI on mistakes, well, you're going to get your AI is also going to make mistakes, and that's a stupid thing to do. With that, thank you so much for the invitation, and if there's any questions, comments, let me hear them.
Okay, thank you very much, Mikkel. So please thank Mikkel for the nice presentation, physically or virtually. Yes, let me now stop recording.